Let's talk a bit more about subsequences in this module. First, let me recall the definition of a subsequence. So if an is a sequence and sigma from n to n is an increasing function, then a sigma n is called a subsequence. It's called a subsequence. In other words, this is just a collection of terms from the sequence an in the same order. So it is an1, an2, so on, where n1 is strictly less than n2, is strictly less than n3, and so on. It is just terms of the sequence in the same order. And a moment's thought should convince you that this proposition is true. If not, the proof certainly will. It's a very easy proposition. If an converges to a, then any subsequence a sigma n also converges to a. So all subsequences of a convergent sequence converges to the same limit. Proof. Let capital N be the function coming from the definition of an converges to a, right? Now observe that sigma n is always greater than or equal to n. Why is this? You can show this by induction. Okay, this is actually obvious to see. Show by induction. This just follows from the fact that sigma is an increasing function. Okay, now if small n greater than n epsilon, then mod a sigma n minus a will also be less than epsilon, simply because sigma n is greater than or equal to n, which is greater than n of epsilon. Okay, and that's it, we are done. So the same function capital N that works for an converges to a also works for a sigma n converging to a. So this was a fairly easy proposition. The next one is a slightly more complicated proposition. It is sort of a converse for this proposition. Now, the naive converse of this is, if every subsequence converges to the same limit a, then the sequence itself converges to the limit a. Well, that is a bit naive and simplistic, because the sequence an itself is a subsequence of the sequence an. Therefore, saying that every subsequence converges to a directly says that an converges to a. It's not really much of a big deal. We can do slightly better by stating a more nuanced version. Let an be a sequence such that each subsequence has a further subsequence that converges to a. Then an converges to a. What this is saying is, no matter what subsequence you take, we are not guaranteed that that subsequence converges to a, but what we are guaranteed is that some subsequence of the subsequence you are considering converges to the point a. In this event, the whole sequence an itself converges to a. And the proof is by contradiction. You have to negate what it means. Okay? Suppose an does not converge to a. Okay, what does this mean? This means This means for some choice of epsilon greater than 0, and every and each, I will not use every, I will use each n in n, we can find small n greater than n such that mod an minus a is greater than epsilon, greater than or equal to epsilon. What this is saying is, there is some epsilon that plays the role of an obstacle that cannot be surmounted. That means no matter what capital N you choose, that will not work in the definition of convergence for this particular choice of epsilon. That means mod an minus a will be greater than or equal to epsilon for some small n greater than capital N. Okay. Now, I want you to prove that this can happen. This can happen only if for infinitely many choices of small n in n, we have mod an minus a greater than or equal to epsilon. Okay, let me just give you a hint. Look at this capital N and keep on increasing it. You will be able to get infinitely many terms small n with mod an minus a not strictly greater than or equal to epsilon. Okay. Now, it's fairly easy. We can construct a subsequence using these n. How do you do that? Well, it's fairly straightforward to do it. At this stage, I can just leave it to you. But let us indulge ourselves and actually try to write down a proof. Okay. Now, what you do is the following. First consider the set of n in n such that mod an minus a greater than or equal to epsilon. Let's call this set S. What we know is this is an infinite set. That's what I have asked you to prove. Okay. Given that it's an infinite set, what you do is you set n1 to be infimum of capital S. Okay. Then set n2 to be infimum of S minus set with S1. And I believe you know what is going to come. Set nk to be infimum of S set minus S1, S2, sk minus 1. And this will give you the required subsequence. Okay. So, you have found a subsequence. We have found a subsequence that cannot converge to A. That's how this subsequence was constructed. That cannot possibly converge to A. This is a contradiction. So that means our original hypothesis that AN does not converge to A is wrong. And this concludes the proof. This is a course on real analysis, and you have just watched the module on subsequences.